Hello everyone! Thanks for joining today's webinar. Before I let you in the hands of our subject matter experts, I'd like to direct your attention to a few elements that will be useful to you. First, your user interface is at the bottom left of the screen. Similar to a chat window, use it to contact us at any time for technical assistance. Watch out for general announcements through this tab. Finally, send us your questions using the Q&A tab in the user interface, as it is the only one directly relayed to the experts. Enjoy today's session.
Thank you, Veronique, for the introduction. Hello, everyone. Thank you for joining, and let's get going with this webinar. As you know, Edify has been pioneering portable TFM since 2013. So the speed has been improved from a quarter inch per second in early 2013 up to 4 and plus inches per second in 2020. Regarding the TFM option, there was only one available in 2013. Today, if you look at the capture options for TFM, you got more than 10 options that you can custom to meet your inspection requirements. If you look back in 2013, there was absolutely no standard for TFM. Now there are a couple of standards, and not only there are standards for TFM, but we are code compliant. So today we release the version 3.1 of Capture, which is the software available on Gecko, Mantis, and the PC version. So the download link should be available for our customers online shortly. This version is brings numerous improvements on ergonomy, analysis, and TFM tools, and that's today's focus. We are going to present improvements in speed and code compliancy with a weld inspection setup that is presented here. So yeah, so I've got a Gecko here. There is a probe and an encoder. The probe is a 5 MHz 64 channel probe, phased array, and there is a shear wave wedge, and there is a string encoder on the test plate. And that's where I'm going to switch to live screen capture. So now I've got a webcam showing the experimental setup, and you should see the capture interface as well. So here I'm going to load all the equipment I'm going to use. So here's a weld plate, 25 millimeters, so 1 inch thick. I can edit that just to show you one new gimmick we've added on the weld. It's the ability to display or not the heat affected zone. So here I've got a has along the chamfer that is about 6 millimeter, which is a quarter inch wide here, so I can display it on the 3D. If I rotate my plate, I've got a full view of my geometry, the geometry I'm going to inspect. Okay, for the plate on the probe, I'm going to load one from us. Here we go, this guy. So it's a 64 element 5 MHz probe with a wedge, and I'm going to quickly check the wedge calibration. This is a feature that most of you know now. It's very handy whether to check the manufacturer specs or just to account for wear and tear on your wedges. So let me go to angle height calibration here, and I think I've got enough gain, so let me adjust this gate here to make sure I've got all the echoes of my probe. I go from element 1 through 64 here. It's also acts as an element check, and then to make sure to measure my my probe, my wedge actually, I just click on measure. So now it says measurement successful. In one click you've calibrated your wedge, and it shows 36.4 degrees, and sound pass from the middle of the probe to the exit point, it's 35 millimeter roughly. But here these values, when I click OK, they are updated onto the wedge directly here, so you don't have to type it in. It's already saved here in your setup. So if you save this probe with a date, today, there you go, Now it shows it's got a new name and it's been calibrated. So you can actually be very precise for TFM imaging with this wedge calibration. Final step on the equipment. Let me load a scanner here. I'm using a string encoder from EcoScan, and there it is. It loads the points per distance, either in millimeter or in inches. I'm using millimeter today because I'm inches impaired, but here you can check the resolution here. You can calibrate it, and here for the scan, I've actually rehearsed this webinar, so it's I know I'm going in the right direction with this polarity here. Which basically now I've got a green check on the equipment. I can tackle the TFM settings, and that's where we're going to spend more time just to explain the differences with the TFM options. So right now, let me just click on the orange button. I just follow this interface orange button. Edit the TFM settings. So here I've got basically I've got my probe. The 3D rendering is still here. I can show the 2D view here, the side view. I'm just going to adjust the offset. There we go. And basically what I'm doing is I'm setting up a zone. That's the only thing I need to tell the software to produce a TFM image. I tell him where to compute the image. So that's the width of the zone, and that's the height of the zone. So basically I'm taking direct shear wave both in the first leg and the second leg. So technically I'm imaging at the same time TT modes and 4Ts modes here. So I press compute for TFM FMC. You can see this this is the regular, probably the most known today option of TFM, and that's the FMC capture. So let's compute it. And now, since I'm here, my probe is coupled to the calibration block, and I can visualize my 3 sideways holes here on the TFM image. Okay, now things start to get more interesting. Right now I can check my max scanning speed, so if I click here, it's kind of slow with the full FMC TFM image. I got 32.5 millimeter per second, which is 1.5 inch per second. So, but we're going to see in a minute how we can speed that up. But right now I want to come back to one of the most innovative feature of Capture 3.1, which is the amplitude fidelity feature, the code compliancy, if you like. So right now, I'm going to click this button. That's a new button on the Capture interface, and it's called the grid verification. And now, so basically I'm entering a mode where I can put a zone here on my reference reflectors. I can put a threshold to make sure I'm above the threshold to detect the maximas, and I can compute this amplitude fidelity to actually measure it. So I'm not talking about a theoretical estimator. That is not what the codes are asking. Codes are actually asking for a proven amplitude fidelity, which is what we are doing now. And here I'm doing it in the middle of the hash for specific offset. So basically what the software is doing, it's computing many TFM images, actually 20 here on this window with a step of a 20th of a wavelength. So it makes sure basically the software is checking that the amplitude doesn't vary more than 2 dB for each grid variation. And now here for this middle zone, I've got like a code compliancy. It's screen check here, and I'm within basically less than 1 dB variation. If I click OK, I can actually visualize the amplitude table, which is also what the codes are asking to prove that you've got like the amplitude variation for each reflector and each offset. So you can copy and paste this table into your report just by a screenshot. And now, okay, I'm going to move the probe over there. So let me check that here. So right here, so I'm going to basically do it do that again on the near side of the hash. And all I need to do is grab this zone here and reset, recompute. So it's going to take a minute. Basically there's 20 TFM images, still the same, incrementing by very short, very small step, 20th of a wavelength here, doing many images and recording all the amplitude for each variation of the grid. And here, so I'm on the near side, it's a bit less favorable than before, but still, I'm still passing the code compliancy, which is less than 2 dB. So I click OK. Very happy here. I can do it a third time here, which is on this far side of the heat affected zone. So let me move the probe around here. Alright, I'm going to check my threshold. Still there, still valid. Make sure it's still coupled. Alright, and I'm going to click that again. Right here. And let it perform. Alright, so here you can see on the far side, that's a lot easier to maintain amplitude. And that's again one example of the need for actual measurements of the amplitude fidelity. So if I click OK, here I'm happy, I've got the amplitude table, I can click OK, and back here, now I've got a green check here, which tells the user that the grid is well defined for the amplitude setting, for the amplitude fidelity. Now if you click on the TFM option, we've got the auto mode that ensures this value of the grid size based on the theoretical value, and ensures to maintain basically the amplitude fidelity within 2 dB. As you've seen, you've got a different value whether you are close to the near side or close to the far side or in the middle of the hash. So what we do here, since we're measuring, we can actually decrease the number of points and still check our amplitude fidelity, which being more precise than using a theoretical value that is wrong if you're not centered, then you can reduce the number of points and go for a much faster inspection. So let's compute the image with, instead of 167k points, let's do one with 93k points, and see if we let's go in this case, for instance, see if we still have amplitude fidelity here. Oops, there we go. Grid verification and compute. Less points in the image, it should be a bit faster. There we go. So now we got still 0.8 dB, so we're still way within the tolerance, and we click OK and press OK. So if I click OK here, oh sorry, I wanted to show you the speed. So now instead of going 35 millimeters a second or 1.5 inches, now I'm more than 2 inches per second. Still using TFM, elementary FMC capture, and code compliance. Okay, now I want to show you something, another gimmick we're just releasing with Capture 3.1. That's the plane wave imaging option. So hang tight, that's gonna shock some of you guys. So let's forget the number of points. We've seen that with the amplitude fidelity. Now I'm going to switch from elementary FMC to plane wave imaging. So let me see that. So I'm just going to say one brief word here before sending you guys to this article here. My esteemed colleague Fred Reverdy published this online on our website Identify, where it explains all the details of the options of TFM, notably the differences between full matrix capture and plane wave imaging options of TFM imaging. So I'm just going to say one word here. One method is omnidirectional. That would be the regular FMC, and one is more directional with plane wave imaging. So I'm just going to leave it at that. If you want all the details, please go check this article out, or one of the many articles Fred has on LinkedIn as well, or on the corporate website. So for the TFM option, now I've clicked plane wave sectorial, so let me see the options here. So I'm not going to touch the manual options for the grid here. I'm going to do focus on this TFM mode that I can use standard or custom. So here on the custom, I can see my initial directional beam steering from 36 to 85 degrees with a couple of 8 shots here, and that's my zone coverage. You can see it on the first leg and also on the second leg. And now I'm going to compute this TFM image. So let me alright, so that's the plane wave imaging option. So plane wave imaging, and that's what I want to show you here. That's the speed. So now the speed estimation is about it's 96. I'm sure if I increase maybe one shot less, I could reach more than 100 here. But basically, I'm almost 4 inches a second here, which is comparable to phased array scanning speed, except you have more all the advantages of TFM. One of them is tolerance to positioning, the other is resolution for characterization. You got many advantages. I'm not going to go through that now. I'm just going to show this plane wave imaging option and see what it brings to inspection. So here you got like the TT mode. Again, you got the TT mode in the first leg and the 40s mode in the second leg. I can also do a grid verification on this guy. It's the same principle. The interface is exactly the same whether you are in FMC or plane wave imaging option. I'm just going to do that again for this setting here. There we go. Now we got like so still within the 2 dB tolerance. So I'm passing the amplitude fidelity test. I've got my amplitude table. I click OK, and I've got my green check here, so I can peacefully go to the next step of the capture interface. I've got a what speed am I achieving? Oh yeah, sorry. Let me go back here. I'm close to 4 inches a second, and I'm code compliant. So actually, I'm not going to do repeat the near zone and the middle zone, but with the setting, if some of you wants to see it, I can send the other videos. But let's save some time here and go on with the other options. Another recommended practice for well inspection is the use of TCG. All the inspectors in the audience know it. It greatly helps detection and analysis. So not only TCG but also ACG, so both time and angle correction gain. And here I'm going to show you our automated wizard, 3-click wizard that does that for you. So it's going to, for those of you who are already familiar with it, bear with me. It's going to take a couple of seconds. So I'm going to just activate it and go on the sample. So I'm now on the sample, and here, so I make sure I've got decent amplitude back and forth. Alright, so let's click play right here and start gathering data. Okay, I've got data now, so I press stop here. I press next. can adjust my zone, make sure that the right thickness, the right depths. Yeah, 3 zones simultaneously, and in one more click, the TCG is done. There it is. You can check for the amplitude table that is automatically saved for your report, and you can go check. If I scroll my TCG from left to right, I got my amplitude per line. So it's all been corrected. Now I can manually check it. If I'm not too clumsy, I should get 80% amplitude for each of the holes. Alright. So I'm going to save this. You can save the CCG for later use, which is very convenient for field inspection. You can save and reload your TCGs as long as they are compatible with your probe and your number of shots and number of grid settings. You should be able to reload it. And press OK, and that's it. Your TCG is done. Alright, let's move on to the actual plate to scan. Starting to get fed up with these sideway holes here. So let's see TFM in Wales. So I'm gonna go click next here and set up put this probe onto the specimen here, and I'm gonna check my motion here with my so here's a 3D view. Let me check this scanner. Alright, so basically I've got a trajectory goes from 1 to 270, which should be towards the end of the plate, should be good enough for demo. Alright, 3D view, 3D rendering, so you can see the zone coverage here. Okay. The layouts, so here I've got like up to 4 layouts, so you can display the things the way you like it or your colleagues like it. So here I've got 4 layouts: Alice, Bob, Carlos and Diana. So Alice likes the T-scan on the left, C-scan on top, T-scan in the middle, and side view at the bottom. Bob likes side view and a 3D view. Carlos likes the C-scan on top, and so on and so on, so you can really customize and save your layout. Okay, final options before getting to data acquisition and inspection, the recording options. We've been gathering or compiling all the data from most inspection reports. You can customize it, preload it for later use in the field. Here's a preview of the report. Right, there we go. So it recalls all the essential variables. Your TCG, that's why it was so long. I added the TCG, otherwise you can remove it. It's going to be a bit quicker. There we go. There we go. Now we're ready. We can save that to our inspection file, and now we've got a fully configured file that you can just recall next time you reload the gecko. Let's go to inspection. And Alice, Bob, let's do, let's see, juice it up a bit. Coupling. No matter how fancy the technology, at the end you just need coupling. Alright. So here, just quickly checking my settings here. So my root, there we go. You can see here I've got like nice toe crack here for first leg and second leg. Take that phased array. And what else? Macrofusion near side crack, toe crack, and porosity again. First leg and second leg. Alright, let's do a quick scan and make sure you don't blink. It's going to be very quick. So let's do this one. Alright. So I'm just going to type this here. Yeah. Alright. Click 0, reset the coder, and press play. and action. Here we go. Oof, done. Save and ready for analysis. Alright, so I'm here in the acquisition panel, and we're going to talk about readings, indication table, and auto sizing. So let me grab this here. Here, so let's navigate the scan. I don't know, let's find the toe crack here. I can crank the gain a bit more. There we go. So yeah, so that's the toe crack you could see on the first leg, and also mostly on the second leg, of course, but also on the first. Right here, and then the indicators. So here I can customize my readings, say with the world centerline distance in millimeter, for instance. This one with the world centerline distance in inches, and so on and so on. So you can, the depths, why not? Do depths here, and then true depths should be, here we go, makes sense. So that's, so I can go pick up this echo right here and see, so the 2mm depths, 48 double. Alright, does the operation for you. You got the distance in from the weld center line in millimeters and in inches. And of course you can customize this. You can also, let me show you briefly like a couple analysis feature we've brought with the auto sizing. So you can really configure your thresholds in the custom button here, and you can do some sizing on an indication. So right now, if I zoom in, I can see the 6 dB contour, so the box snaps to the actual 6 dB contour, or whatever dB value you've entered in the auto sizing feature. So I'm going to stop here, and yes, of course you got the indication table after that. So here you can load preset, you can configure by your application. So here I'm going to open one that was prepared by our level 3 here, and I press OK, and I've got the indication table with my selected indicators, namely scan start, lens, world centerline distance, true depths, and so on. I can scroll this and then export the table as a PDF or as an Excel file. Alright, I'm going to stop here for the analysis features. We've added a bit of ergonomy, and before concluding I'm just going to show you the 3D view here. So let's see, so basically here on the offset, you can just, without having to rescan, you can change the offset here. You can see the weld overlay follows, so actually my offset was good. I can recenter the weld on my data, so I don't have to rescan, I can just correct offsets, overlay, thickness, things like this without having to rescan. And finally, just as a teaser, I can show you the 3D view here. So here, so not only like the T-scan could be display, the slice, or the full 3D of the data. So here you got the, let's see all your indication, your data projected onto the 3D view. So you have the side view here, you can really see the crack, lack of pen, far side, lack of fusion, and the toe crack here that you can barely see on the first leg as well. Alright, time to wrap up this today's webinar. So here are the conclusions presented here on this slide. So what we've seen today on the new features of Capture 3.1 is that we can actually do a 1 inch thick a weld inspection with TFM, code compliant at about 4 inches per second. We've seen also barely glanced at it, but the analysis feature released in the Capture 3.1 are presented in the same environment as the data acquisition software, which makes it basically training free for the users. Just want to thank you all for listening today. I'm gonna forward you to our website for more application notes and all the other features of 3.1 that you're gonna see online shortly. Thanks again. Thanks for bearing with me. I'm gonna stay here for a couple of questions online, and see you guys next. Bye bye. Okay, let's see some questions here. I'll start with what's the maximum speed that can be achieved with TFM? Yeah. So it really depends on many parameters, such as the number of channels, the number of points in the grid, or even the sampling frequency. In the example presented today, we've shown a 4-inch per second speed for the inspection of 1-inch thick V-weld using a 64-element probe. If we were using another example, say half an inch thick weld with a 32-channel probe, we would have reached 8 inches per second and more. So as you see, the TFM scanning speed can even be faster than phased array UT now. Now let's see. How many elements can I use with TFM? With a top-of-line gecko, we can use up to 128 elements with TFM, which is unique in the marketplace. We are the only one doing this on a portable unit. To give you an idea, this allows to reach more than 1 meter focusing in steel using a 5 meg airwave probe with the right aperture. So okay, let's go for the final question here. What are the differences between TFM options regarding resolution? I would reply it's application dependent. For weld applications though, plane wave imaging shows the same resolution, better signal to noise ratio, better speed, and better dynamic range than FMC. For near surface resolution and contact applications, however, FMC TFM would provide better results than plane wave imaging TFM in some cases. I invite you to check Frederick's blog on the Edify website for technical insights on the specifics of both techniques. But that said, Capture is the only portable TFM interface that allows the technique to be tailored to speed and resolution requirements of your inspection. And as you've seen during this webinar, we keep it in a super friendly environment. Okay, we've already crossed the half-hour duration. I'll stop here. Contact us directly if we missed your question, and please check our online presence for recordings of this webinar and more in-depth articles about our technology, products, and applications. Thank you all for attending. See you guys soon.
And that concludes our session. Thank you for your time today. Know that this webinar session has been recorded and will be made available shortly on our website. Do not hesitate to reach out to us via email at info@edify.com. See you next time.